We have a firm belief in the fact that matter comprises particles. Can you see what I am writing on the blackboard? Is it visible? Ali, आप दरमियान में आ जाए तो बेहतर होगा. Around 1896, J.J. Thomson showed that an electron is a particle and it has a certain charge to mass ratio. He performed the famous experiment on discharge tubes. But his own son, G.P. Thomson, in the 1920s showed that the electron actually behaves like a wave. तो ये बाप और बेटे के दरमियान ये कश्मकश सी है. आप ताजमहल किसने बनाया? शाहजहां ने. लेकिन उसके अपने बेटे औरंगजेब ने उसे कैद कर दिया आगरे के किले में, और फिर वो एक छोटी सी खिड़की में से ताजमहल को देखता था अपने कैद खाने की. तो बिल्कुल उसी तरह की कहानी है कि जे.जे. थॉमसन ने बताया, उसने फैसला कर दिया कि an electron is indeed a particle. It carries momentum, it has a charge to mass ratio, and the sun comes in about 20 years later and showed that the electron in fact behaves like a wave because it undergoes a phenomena that we call diffraction. If you recall from the first lecture, we described a very important experiment in physics that was ranked as the greatest experiment in physics. And we showed that an electron behaves like a wave. It indeed behaves like a wave. And even if there is a single electron passing through the double-slit interference experiment, even a single electron behaves like a wave. And it interferes with itself. What is this wave? And what is waving in this wave? देखो, जब हम sound waves की बात करते हैं तो we are talking about compressions and rarefactions. We have regions in space which are compressed, which have a higher pressure, followed by regions which have a lower pressure, followed by high pressure regions, and so on. So there is something that is waving in a sound wave. And what is waving? It's the air pressure. It's the air pressure that is fluctuating in space and fluctuating in time. So in a sound wave, if we have time here and we look at a certain point in the medium and we plot the pressure of the air, we will get a wave-like behavior. So in a sound wave, we know that the amplitude of the wave is in fact the pressure of the air. In water waves, what is waving? The amplitude or the height of the wave. That is the property that is waving. So whenever we talk about a wave, a traveling wave or a standing wave, there's a concept that comes in our mind. There is something that is fluctuating with time, something that is undulating with time, that is changing with time. Right? We know that. But when we talk about an electron acting like a wave, what is the nature of that wave? And what is really waving? Okay, so that's the fundamental question that we would like to answer today. And we would also like to look at an experiment that indeed shows electrons really act like waves sometimes. So in 1923, a French PhD student, Louis D. Broglie, or Louis D. Roy, he was writing his PhD thesis, and in his thesis he showed that any particle that carries energy E and has a momentum P can act like a wave. When something acts like a wave, it must have a certain frequency and a certain wavelength. equals hf. अगर हम एक फोटोन की बात करें, फोटोइलेक्ट्रिक इफेक्ट ने हमें बता दिया कि a photon is a particle, it carries energy. Compton effect ने हमें बता दिया कि a photon has momentum as well, and the momentum of a photon is p. The energy is also related to the momentum through E equals pc for a photon only. ठीक है? अब सवाल ये पैदा होता है कि the photon has energy और हम लिख रहे हैं कि energy equals hf, but f is a wave-like property. In order to define f, you have to draw some wave, and it varies in time, and the time interval between these two crests is given by the time period whose inverse is the frequency. So when we talk about frequency, we have to associate in our minds a wave with it, but this is a particulate quantity, energy. Similarly, when we talk about momentum, it's associated with the particle. We also know from relativity that a photon travels at the speed of light. It travels at c, at the speed c, and f is given by c over lambda. So this is a very simple reasoning that de Broglie used. देखो बहुत simple mathematics है. Energy equals hf, f equals c over lambda, but the energy also equals E times c. These relationships are well known. So if you compare these expressions, you immediately recognize that P equals h over lambda. So now you have a momentum of a particle, and associated with the momentum of the particle is a wavelength, which is a wave-like property. Here you have an energy, which is a particle property, and a frequency, which is a wave property. So you have a relationship between a particle and a wave property. Here you have a relationship between momentum and wavelength. In order to understand what wavelength is, we draw a wave, and now the x-axis is simply distance. And now the distance between two successive points that are in space is defined as the wavelength. So this relationship, P equals h over lambda, is called the de Broglie relationship. अच्छा, यहाँ तक बात बिल्कुल क्लियर है. ये आपने पहले भी पढ़ा होगा A levels में, FSC में. ये बात बिल्कुल रोज़े रोशन की तरह आपके सामने है. इसमें भी कोई शक नहीं है ना? अच्छा. A photon, that is a particle, it is moving at a certain speed through space. So if we, in our mental picture, if we think of the photon as a sphere, as a particle, and it's moving in vacuum, if you take a picture of this photon, and then you have a high speed camera, you take a picture of the same photon after a time t, it will have moved in space through a distance ct. And you know that the photon is now here. The particle has now left its original position and moved at a different point. And that is because you can identify the photon as having a spatial extents. A photon exists at a certain point in space, and it doesn't exist everywhere. But when we talk about a wave that is traveling in space, the picture that we draw for a wave is something like this. You take a picture, you have a camera, and suppose that camera can capture waves. The camera takes a picture, it captures a wave. After a certain lapse of time, it captures another wave. It captures another wave. But this wave is spread out in space. So these two pictures of a particle and a wave do not reconcile with each other. There is some dichotomy. there is some conflict between these pictures, between the picture of a particle and a wave. But we know that the photon has frequency and wavelength, so it must be a wave. And we know that the photon also acts like a particle because there are experiments to back up this statement. So what really is light? What really is a photon? And this is a question that is answered through wave-particle duality. That is, a photon is a wave and a particle at the same time, and whether it manifests itself, it shows itself as a wave or a particle, depends upon the kind of experiment you perform. For example, in our two-slit experiment, if we decided not to see which slit the electron is passing through, then the electron is acting like a wave. But if we try to be over clever and over smart and try to figure out which slit the electron is passing through, the wave behavior disappears and it starts acting like a particle. So whether an electron is a wave or a particle, this is a bogus question. ये क्वेश्चन कोई मान ही नहीं रखता, ठीक है? इलेक्ट्रॉन की कोई ऑब्जेक्टिव एग्जिस्टेंस नहीं है as a wave or a particle. An electron sometimes shows itself as a wave. एक बहरूपी इलेक्ट्रॉन, कभी कोई दो उसके चेहरे हैं, कभी वेव का मास्क पहन लेता है, कभी पार्टिकल का मास्क पहन लेता है. उसकी ऑब्जेक्टिव एग्जिस्टेंस वेव या पार्टिकल की सूरत में ऐसे नहीं है. You perform a certain experiment and an experiment can reveal its wave properties and an experiment can reveal its particle property. ठीक है? तो ये है wave particle duality. Now let's talk about an experiment that actually shows that electrons are waves. And an experiment that was performed in 1923 by Davison and Germer. The Davison-Germer experiment. लेकिन पहले इसके कि मैं आपको डेविसन जर्मर एक्सपेरिमेंट के बारे में बताऊं, जाहिर है नील्स बोर ने 1913 में अपना मॉडल पेश किया था और उसने कहा था कि एंगुलर मोमेंटम इज क्वांटाइज्ड. दिस इज वन ऑफ बोर्स पोस्टुलेट्स. अब उसकी फिजिकल इंटरप्रिटेशन पर हमने भी कोई बात नहीं की, लेकिन लुई डी ब्रोगली ने बताया था कि दिस पोस्टुलेट हैज अ फिजिकल मीनिंग एज वेल, व्हिच मोस्ट ऑफ यू नो. And that physical meaning is that if I draw an orbit for an electron with a radius r, then and the electron is moving in this orbit around the nucleus with a linear speed v, then there is a wave associated with the electron. There is in fact a wave associated with the electron. ठीक है? इस तरह की वेव जो किसी पार्टिकल के साथ एसोसिएटेड हो उसे कहते हैं मैटर वेव. डी ब्रोगली ने इनको कहा था पायलट वेव. अब ये पायलट वेव क्या होती है? इस इलेक्ट्रॉन के साथ वाबस्ता एक पायलट वेव है या एक मैटर वेव है जो इलेक्ट्रॉन के साथ साथ घूम रही है. ठीक है? So it is the wave is piloting the electron. इसलिए इसको पायलट वेव कहते हैं कि ये वेव इलेक्ट्रॉन के साथ साथ चल रही है और इस वेव की वेवलेंथ ऐसी होनी चाहिए कि the circumference of this orbit captures an integral number of wavelengths. So when you perform an experiment in which you excite vibrations on a string, standing waves are produced if there are nodes on the ends, which means the length can only hold an integral number of half wavelengths. That is when standing waves will be produced. Similarly, if the circumference holds an integral number of wavelengths, only can such a wave be sustained. Because if this condition does not hold true, The wave passes through the orbit once, and when it comes through the orbit in the next cycle, it will destructively interfere with the previous wave. And when destructive interference takes place, the wave just fizzles out. It just goes to zero. So in order to have a sustained wave associated with the electron, this condition needs to be satisfied. And if you look at this condition, let's put 2 pi r is n over lambda. If according to de Broglie, I can write n lambda is h over p, which is mv, 2 pi r. So I take the mv to the other side, I get mvr is nh bar, which is precisely Bohr's quantization of angular momentum condition. So de Broglie gave a physical interpretation to Niels Bohr's condition of the quantization of angular momentum. Alright, so this is something that I wanted to tell you before I move on to Davison and Germer's experiment. Alright, so Davison and Germer's experiment was an extremely complicated experiment as far as this experimental skill was concerned. Now, what was the experiment all about? Does everyone know what diffraction is? Diffraction का पता है सबको? Attracting the electrons. So this is negatively charged, and this is positively charged. So this is the anode, this is the cathode. The electrons are being attracted downwards, and this voltage V0 is variable. Now on this anode is placed a piece of nickel. एक निकल का एक पीस पड़ा हुआ, निकल एलिमेंट है ना, मैग्नेटिक एलिमेंट है एक निकल, ठीक है? The electrons strike the metal, and inside the glass jar there is another slit, and attached to this slit is a detector of electrons. And a suitable detector, as you all know, is a phosphor screen fitted with a microscope that can see what the intensity is. And this particular detector D can move in a circle. It can move in a circle. This angle, say, is 0 degrees, this angle is 90 degrees. So it can move in a circle from 0 degrees to 90 degrees. So what the experiment is all about is that the detector is fixed at a certain angle, and it is measuring the intensity of the reflected electrons from nickel. So electrons strike the nickel target and they are reflected or scattered, and this detector picks up the electrons that are scattered through a certain angle theta and finds the intensity of those electrons, the number of electrons reaching the detector per unit time. So the angle theta is varied and no pattern is observed. No pattern was observed. The angle theta was varied and no pattern was observed, which means that theta was varied. Theta was varied from 0 degrees to 90 degrees, and the intensity of the scattered electrons remained more or less constant. Now what happened by accident? बाज़-ओ-क़ात हादसे किसी बहुत बड़ी कामयाबी का सबब बनते हैं, और यहाँ पर एक हादसा हुआ. हादसा ये हुआ कि the experimenter dropped some equipment on the glass jar and the glass jar broke. ठीक है, ये जो शीशे का जार था ये टूट गया. When the glass jar broke, the vacuum broke. There's no vacuum. Air rushed inside and everything, and there was all air inside now because the jar had broken. Now these experiments were being performed at elevated temperatures. High temp, यहाँ पे एक हीटर भी लगा हुआ था जो इस निकल को हीट अप कर रहा था. Now there is air in the vicinity of nickel and it's at high temperature. What will happen to the nickel? It will oxidize. So the nickel oxidized and nickel oxide was formed. Now the experimenters, Davison and Germer, wanted to remove the nickel oxide. They wanted to have nickel again. So what they did is they wanted to reduce this oxide back to nickel. देखो ये हादसे हो रहे हैं, कुदरत उनसे कोई काम ले रही है. This nickel oxide they had to reduce back to nickel. So they flowed hydrogen on top of the nickel oxide and very slowly heated the nickel oxide. Extremely slow heating. And when they slowly heated the nickel oxide in the presence of a stream of flowing hydrogen gas, the nickel oxide was reduced back to nickel and water vapors were formed. Okay? And why did they have to do slow heating? Because hydrogen is flammable. Hydrogen is flammable, आग पकड़ लेती है. So they had to be very, very careful and patient and cautious about heating the assembly. So they very slowly heated the nickel oxide in the presence of a flowing stream of hydrogen, got back nickel, established the vacuum again and performed the experiment again. And when they performed the experiment, they observed a very wild behavior. At theta equals to 50 degrees, they got a strong peak of the reflected intensity of electrons. And the voltage that they applied was 54 volts. So for a voltage of 54 volts, they got a peak around 50 degrees and it was a broad peak. So what's going on here? So first of all, let's see why did they get a peak at 50 degrees for a voltage of 54 volts. It seems a very strange coincidence. You change the voltage, the position of the peak changes. But there is definitely a peak. So there is something special about 50 degrees and the 54 volt combination. There is something special about it. You apply a different voltage, you get a peak at a different position. So there is something special that is going on here. And how did they? First of all, let me give you a mathematical reasoning of what is happening here. And then I will tell you how this oxidation and reduction cycle actually made the experiment work. Atoms is A. It's a crystal. Now what is happening is if electrons are falling onto the nickel target, these atoms, this plane of atoms will reflect the electrons. So this plane of atoms on the surface is acting like a reflection grating. It is reflecting the electrons. And when the electrons are reflected, they can, and if these electrons are acting like waves, then these reflected waves can interfere with one another. And they can interfere either by constructive interference or destructive interference. And constructive interference will take place when the path difference between the reflected waves is of the correct magnitude. And the path difference between these reflected waves is this much. This is the path difference between the reflected waves. Agreed? So if there is a parallel beam of electrons and those electrons are acting like waves, the waves are being scattered or reflected from the surface atoms which form a plane, and if these reflected waves are in phase, they will constructively interfere to give you a large intensity, and if they are out of phase, they will destructively interfere and give you a smaller intensity. So if this distance, which is the path difference, if this is A and this reflected angle is theta, if this angle is theta, this angle is theta, and this length will be equal to A sin theta. This length is equal to A sin theta. And whenever this length, this path difference A sin theta equals an integral number of wavelengths n lambda, constructive interference will take place. Alright. So let's take n equals 1 for the first order of reflection maximum. So A sin theta equals lambda. Now, if this is the velocity of the wave, if this is the velocity of the particle carries a momentum. And if we apply de Broglie relationship, one can find the wavelength corresponding to this velocity. And the wavelength will be given by h over mv. So can you find this value for me? H is 6.63 into 10 raised to power minus 34 joule seconds, or m is 9.1 into 10 raised to power minus 31 kg, and the speed is, you've already calculated the speed. Can you find out the wavelength for me, please? जी.
So momentum की हम कौन सी definition use करेंगे?
Sorry?
Momentum की definition relativistic use ही करेंगे.
देखो ये जो speed है, it's 2 orders of magnitude smaller than the speed of light. So we're using the non-relativistic expression. Can you tell me what the wavelength of the electron wave is? Uh, 1.6 angstroms. 1.6 angstroms. And can you find the value of A from lambda over sin theta, where theta is now 50 degrees? जी 2.1 angstroms. So the spacing of the atoms, the nickel atoms in the crystal is well known, because X-ray diffraction had been discovered in 1912 or 13 by Bragg. X-ray diffraction had been studied, the spacing between the atoms was well known, and the spacing was indeed 2.1 angstroms. So corresponding to a voltage of 54 volts and an intensity maximum of at 50 degrees was indeed expected if the electrons were behaving like waves, and they possessed a wavelength given by h over mv. So this is how Davison and Germer showed that an electron with a certain momentum, which is conventionally taken to be a particle, is actually acting like a wave as well, and it has a wavelength, and the wavelength is precisely given by h over mv, or h over the momentum. So electrons can be diffracted because they act like waves. Protons can be diffracted. Neutrons can be diffracted. All of these particles, which we think of conventionally as being particles, they can be diffracted because they act like waves. But the question remains, we're talking about matter waves, but what is really waving here? And how do we reconcile the concept that we introduced on the first blackboard, is that a particle has a finite spatial extent, it starts somewhere and stops somewhere, whereas a wave extends. Generally our conception of a wave is that it extends throughout space. So now we know that the electron is a wave, but we don't know what the wave is. What's the nature of the wave? And what is waving in the wave? ठीक है? कोई एप्लीकेशन आप बताएं इलेक्ट्रॉन्स एक्टिंग एज वेव्स. इलेक्ट्रॉन माइक्रोस्कोप, शाबाश. An electron microscope is a device that takes an image of an object, a biological object, a bacterium, a virus, a nanoparticle, a silicon chip, a transistor, a microelectronic device, anything you can think of, with the help of electrons. There are different kinds of electron microscopes. You can have a transmission electron microscope, you can have a scanning electron microscope, you can have a scanning probe microscope. There are different kinds of electron microscopes, and they can achieve magnifications up to 1,000,000, especially the transmission electron microscope, and it can go down to the level of atoms. In fact, it can look at less than a nanometer, a transmission electron microscope. So the transmission electron microscope or the electron microscope exploits the wave property of electrons, and it can form an image exploiting the wave properties. लेकिन अब देखिए, ये तो हमने एस्टैब्लिश कर ली कि these particles are waves, but now let's try to answer the first question, the question that we raised on the first blackboard. What kind of wave are we talking about? ठीक है, अब इस क्वेश्चन को हम सॉल्व करने की कोशिश करते हैं. But in order to solve this question, we have to go a little bit deeper into mathematics and use the concepts that you are learning in your course Waves and Optics. Probably you're taking that course. Alright? But you've already studied what waves are. You know what interference is. So we're not going beyond that. But we'll have to take the support of mathematics in order to understand what kind of wave are we talking about. But let me give you the final result beforehand. Suppose you have a particle which is located at a precise point in space. This particle is located here. I've drawn the particle at a certain point on the blackboard. Now associated with this particle, the matter wave cannot be extended throughout space. I would like to have a wave whose amplitude is confined to the region close to this particle. So I would really like to have a wave that is zero everywhere, but close to where the particle exists, it peaks and then disappears. This is what I would like to have. Associated with this particle, I don't want to have a wave of this kind. This is a wave, but this is also a wave. I want to have a wave which resembles this form. And when the particle moves forward, when the particle comes here, this pulse or wave packet, इसको pulse भी कहते हैं, wave packet भी कहते हैं, this also changes its position and comes here. So this pulse as a whole is moving with the particle. So I want to associate a wave with the particle, not a traveling wave which extends throughout space, but a pulse or a wave packet. ठीक है, तो जो इसकी वेलोसिटी है इस पार्टिकल की, Suppose the velocity of this particle is v. I want this wave packet to be traveling with the same velocity v. I want this wave packet to go along with the particle. ठीक है, यही एक legitimate तरीका है पार्टिकल और वेव को आपस में नथी करने का, आपस में जोड़ने का, तभी ये वेव डिफाइन कर सकती है पार्टिकल को. ठीक बात है. अब इस वेव की फ्रीक्वेंसी क्या है और इस वेव की वेवलेंथ बताइए चले, क्योंकि हमें पता है कि एवरी वेव has a frequency and a wavelength. So this particle has a momentum p, it must have a wavelength h over p. This is the wavelength of this wave. But does the wave appear to have this wavelength? Can you tell me what the wavelength of this pulse is? Can you tell me what the frequency of this pulse is? Not evidently. It's not obvious. अच्छा मुझे आप बताएं कि आप ज़्यादातर इलेक्ट्रिकल इंजीनियरिंग के स्टूडेंट्स हैं ना? आप सिग्नल्स एंड सिस्टम्स पढ़ रहे हैं? अभी नहीं पढ़ रहे. Rate this pulse. Now just raise your hand if you know the answer, or you can conjecture what the answer is. आप बताइए. Tuning forks. Tuning forks है. Tuning fork में भला क्या होगा? Tuning fork में एक टाइम के लिए ये वेव जनरेट होगी, ठीक है, और फिर ये डैम्प कर दी जाएगी. This is what the wave from a tuning fork will look like. It will generate a frequency and it will damp with time. तो ये नहीं. कोई और एग्जांपल, कोई और तरीका? आप बताइए, पीछे बैठा आपने हाथ खड़ा किया, बस हाथ वैसे उठ गया ऊपर.
What about a gunfire?
शाबाश. अच्छा आप बताएं, आप हाथ खड़ा कर रहे थे.
So short burst of light.
Short burst
of
okay,
light.
this is a short burst of light. You're giving me the physical reasoning. A short burst of light.
Like a pulse where basically you light
Right.
starts and light ends. Like
That's a pulse, exactly. That will have a form similar to this. But what frequency would it have? Or
there are two frequencies, the higher frequency and the low frequency.
right. Someone mentioned the word beats. So let's look at beats a little bit. Beats के बारे में थोड़ी सी बात करते हैं. With a wavelength lambda 1 and a frequency omega 1. Omega 1 भी लिख सकते हैं ना, रेडियल फ्रीक्वेंसी. f omega 1 से कंफ्यूज तो नहीं हो जाएंगे. Omega is f 2 pi f. And then you have another wave. With a wavelength lambda 2 and a frequency omega 2. And we also know, remember that we can define a wave number k, which is given by 2 pi over lambda. Okay? Now this wave has an amplitude a. This wave has an amplitude a. Suppose this wave is given by y1, this wave is given by y2. Can we write a mathematical form for y1? y1 equals a. आगे बताइए. Let's say cosine. Cosine omega t. तो x कहाँ गया? A wave has time dependence and space dependence. Both dependencies at the same time. Right. You can have cosine k1x minus omega 1t. ठीक है? Similarly, you can have the amplitude or displacement for the second wave given by cosine k2x minus omega 2t. ठीक है? So what is the velocity of the first wave. अच्छा, इस वेव की velocity को कैसे डिफाइन करते हैं? dy by dt. I'm not talking about the velocity of the particle that is going up and down. I'm talking about how the speed with which the wave is traveling, the propagation speed of the wave. ये देखो इन्होंने एक बात याद रखो, इन्होंने बात की the velocity of this wave is d by 1 over dt. That is not the propagation. आपने बात की ना? That is not the propagation speed of the wave. अगर यहाँ एक particle खड़ा हो रखे तो वो उसकी वेलोसिटी है कि वो ऊपर नीचे एक वो स्पेस में फिक्स्ड है, वो टाइम के साथ कैसे चेंज हो रहा है वो उसकी वेलोसिटी है. बट आई एम टॉकिंग अबाउट द प्रोपगेशन वेलोसिटी ऑफ द वेव.
तो लैम्डा ओमेगा बाय 2 पाई.
ओके, डिफाइन करो प्रोपगेशन वेलोसिटी होगी क्या? डिस्टेंस ओवर टाइम. डिस्टेंस ऑफ व्हाट? देखो आप एक वेव बनाओगे, बिल्कुल मैं ये वेव बनाता हूं. You focus your attention on a certain point of the wave. You focus your attention say on the crest. इस पॉइंट पर अपनी attention focus करें. This is time t1, this is time t2. After a certain lapse of time, that is at time t2, to picture the wave again, this point will have moved forward. This point will have moved forward through a certain distance. So this is the x-axis. This is a picture of the wave at time t1, picture of the wave at time t2. Focus your attention on a point. It has advanced in time, and the distance through which it has advanced will be given by the velocity of the propagation velocity of the wave times t2 minus t1. So the propagation velocity, also called the phase velocity, is defined as the speed at which a certain point on the wave advances forward. That is, you look at the wave at two different times and find the distance between 2 points that are in phase. That is 2 points, 2 identical points. देखो ये वाला point कितना आगे advance कर गया. So this is the meaning of the phase velocity. Okay. Now from k1 and omega 1, can you tell me what the phase velocity is? Omega 1. I can write this as cosine k1 को common लिया x minus omega 1 over k1 t. So now what? Can you identify what is the phase velocity? Omega 1 divided by k1. This is the phase velocity. The phase velocity is k1 x minus bpt. ठीक है? ये बात समझ आई? ये मैकेनिक्स में पढ़ी होगी आपने? इलेक्ट्रिसिटी मैग्नेटिज्म में पढ़ी. So if this is our wave, cosine x minus bt, forget the k. ठीक है? So can at time t equals 0, this will simply be cosine x. So if you picture this wave at time t equals 0, you will get a cosine function. what is this? What is the wavelength? ये कितना है? ये डिस्टेंस कितना है? लैम्डा किसके बराबर है? 2 पाई के, 2 पाई के ना? दिस इज 2 पाई। अगर यहाँ पे मैं k डाल दूं एक और ब्रैकेट्स डाल दूं तो k हमारा 1 है। इस पर्टिकुलर वेव के लिए k is 1, which means that lambda is 2 pi over k, which is 2 pi, which is the correct result. Okay, so I can put a k here, and then this wavelength will be 2 pi over k. So now I have a wave cosine of k times x minus bt, and k is being multiplied throughout, and the wavelength of this wave is 2 pi over lambda, 2 pi over k, as you can see from time t equals 0. Now plot at a later time t, at a later time t, now t has elapsed, t गुजर गया, कुछ वक्त गुजर गया. Can you plot the wave again? Now plot the same wave which is traveling forward in time at another time. इस वेव को क्या होगा? ये स्टैटिक तो नहीं रहेगी ना? At another time greater than 0, this wave will have advanced or gone back. It will have changed its position. So the new, if you draw a new wave, you can get a new picture for the wave. You can get a new picture for the wave. Now suppose you focus on this point, which is at height a. ठीक है? Time t equals 0 पे this ये point इसकी displacement a है ना? Now you focus on the same point. You focus on the same point, displacement a. Can you tell me how far it has gone forward? So this is our wave. कितना आगे गया ये पॉइंट? आप मुझे बताओ, ये सवाल समझ आया मेरा? आप बताओ। सवाल समझ, इसको कैसे हल करेंगे इस सवाल? देखो मैंने एक सादा सा सवाल पूछा कि टाइम t इक्वल 0 पे ये पॉइंट था जिसे मैंने डॉट से जाहिर किया, ये डिस्प्लेसमेंट a पे है। एक लेटर टाइम पे ये पॉइंट आगे चला गया। Now I have to find out how far it has moved forward. That will depend on the phase velocity of this wave. इसको कैसे हल करेंगे? मैथमेटिकली बताएं। बताओ।
Sir, pi divided by 2k. 2 pi upon omega.
2 pi over omega तो wave number है ना? So the simple question: this point has moved forward in time. How far has it advanced at this point in time? You simply equate this equal to a. इसको a के बराबर रख रहे हैं ना? The displacement is a, and you want to find out the time at which the left hand side equals the right hand side. So cosine k x minus bt is 1, which means k x minus bt is 0, which means x minus bt is 0, which means x is bt. So the displacement, the horizontal displacement of this maximum amplitude point is bt. So in time t, this point was at x equals 0. After time t, it has moved forward by distance vt. So what is the phase velocity of this wave? v. So this is a general form for a wave of this kind, which is called a traveling wave, and the phase velocity of this wave is v. And we've already shown that the phase velocity can be written in this form, and the phase velocity is omega over k. अब बात समझ आ रही जी?
सर जो वेव की इक्वेशन थी वो पहले से y इक्वल टू a cos c.
This is the wave equation. Y equals a cosine k x minus omega t. Right? This is the wave equation. I can write this as a cosine k, commonly a x minus omega over k t. But this expression omega over k is equal to the phase velocity vp. So given a wave which is traveling in space, which extends from eternity to eternity, जो हमेशा से हमेशा तक रहती है, वो है ना ट्रैवलिंग वेव, उसकी ये इक्वेशन है और उसकी फेज वेलोसिटी इज गिवन बाय ओमेगा ओवर के. Omega over k. Now we have two waves. One has, they have different frequencies, omega 1, omega 2, and different wave numbers k1, k2. Now when both of them are moving in the same medium, they will interfere with one another. They will interfere with each other. And can you tell me, write a form for y1 plus y2? अभी दो waves हैं. कुछ trigonometric identity लगा के find the interference pattern of these waves. ये आप कर लेंगे. आप कोसाइन उन y1 और y2 को ऐड करना है और ट्रिग्नोमेट्रिक आइडेंटिटी इस्तेमाल की है. ठीक है? This I hope I don't have to explain. Right. So once I get the sum and once I get the difference between the two k's and the two omegas. Now let's suppose that k1 is very similar to k2 and omega 1 is very similar to omega 2. But they are different. K1 K2 के करीब है, यानी एक वेवलेंथ अगर 1 मीटर, दूसरी वेवलेंथ 1.001 मीटर, और एक फ्रीक्वेंसी है 10 हर्ट्ज तो दूसरी फ्रीक्वेंसी 9.999 हर्ट्ज. यानी the wavelengths are not identical but they are very similar. The frequencies are not identical but they are very similar. So if you look at this expression, which is the resultant wave, there are two kinds of terms here. This term, which of these terms, there's a cosine term here and there's a cosine term here. Which one of these terms has a lower frequency? This has a lower frequency because this is a small number, this is a small number, this is a high number. Omega 1 plus omega 2 is a very large number as compared to delta omega. It's almost 2 times omega 1. This is almost 2 times K1 because K1 and K2 are almost similar. But you have a division by 2 as well. But anyway, this is a high frequency term and this is a low frequency term. Now if you want to plot this wave, this is also a wave. ये दो waves का resultant है, ये दो waves का interference wave है. अब इसको भी plot कर सकते हैं आप. देखो wave में थोड़ी सी confusion ये होती है कि इसमें time dependence भी और space dependence भी है. तो time dependence में जो term है उसको frequency कह देते हैं और इसमें जो term है उसको wave number कह देते हैं. Time के साथ frequency है, space के साथ wave number है. जो time और frequency का relationship है वही रिलेशनशिप स्पेस और वेव नंबर का है, इसलिए इस वेव नंबर को स्पेशियल फ्रीक्वेंसी भी कह देते हैं. एनीवेज, कैन यू प्लॉट दिस ऑन योर नोटबुक्स फॉर मी? कैन यू ट्राई प्लॉटिंग इट?
नो सर.
No, you can't? Not at all? Okay, let me tell you what this wave will look like. So if I plot that curve, if I plot y here, this is y, it is y1 plus y2, I will get something like this, which means I have a high frequency wave. This is a high frequency wave. This yellow term, this yellow wave is of the form cosine k1 plus k2 x over 2, यानी ये k एवरेज बन गया k1 plus k2 over 2 plus omega 1 plus omega 2, ये omega average है, ठीक है. So this yellow term that is wiggling at a higher frequency both in time and in space has this form, and you are multiplying this frequency with a smaller envelope, with a smaller frequency envelope. और ये जो envelope है जिसे white से जाहिर किया गया है, this is a slower envelope, smaller frequency envelope, which is of the form cosine delta k x over 2 minus delta omega t over 2. So there is a smaller frequency envelope and embedded in the envelope there is a high frequency wave. अगर आप ये वाली high frequency wave ले लें, देखो, और ये कैसे आया multiplication से? ये high frequency wave will just be this high frequency wave, and you multiply this wave with a smaller wave, a smaller frequency wave which goes like this. You multiply the two, you will get something like, you will get exactly this. So if you multiply a high frequency component, which is this term, with a low frequency cosine wave, that is you multiply this yellow with white, you will get exactly this pattern. Now what we realize is that there are certain regions here, 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 where the wave amplitude has reduced. Where the wave amplitude has reduced. And there are certain regions where the wave amplitude has gone up. So this phenomenon is in fact the phenomenon of beats. This is beats. Now as a homework, what I would like you to do before Monday is I would like you to tell me, what this distance, what is the length of the envelope delta x. इस envelope की length बतानी delta x, और अब हम नेक्स्ट लेक्चर में ये देखेंगे कि अभी तो हमने दो फ्रीक्वेंसीज को ऐड किया, जब हम बेशुमार फ्रीक्वेंसीज को ऐड करेंगे, when we add a large number of frequencies, a large number of Ks, we will get the pulse that we desire. And next week we'll devote to the uncertainty. Thank you.